Hi class, welcome to the next section, chapter 9.3, Trigonometric Substitution. So today we are going to be working with how to make a substitution using a trig function when we are given some sort of an algebraic or rational function to integrate. So before we were making substitutions when we had products of trig functions. So you might think that that was trig substitution, but really it was just integrating trig functions, products of powers of trig functions. So today what we're going to work on is integrating functions that are algebraic in nature, x squares and things like that, where using a trig function as a substitution will make things a lot easier. Okay? So slightly different than the last topic. The math is a little bit more involved, let's say. So let's say that I want to find the following area, right? So let's say I have a circle of radius A, and from the angle 1/4 pi to the angle 2/3 pi, I want to find this area, right? So it's not necessarily from one angle to another because, as you can see, we drop straight down in order to find not a sector of the circle, but just some straight portion, right? So the line along the x-axis has to do with a circle of radius A. Okay. So the equation for a circle of unknown radius, or some random radius, I should say, is x squared plus y squared equals that radius squared. In this case, we're not saying r, we're using a. Um, we're only going to need the top half of the function here, right? This bottom half of the function does nothing. So we can use the positive form of the semicircle, which is basically just taking this equation, solving for y. Normally, we would have the plus or minus functions to give us the top half and the bottom half. But since our area here only has to do with the top half, we will just use the positive semicircle function, right? So that radius squared minus x squared, all under a square root sign. Okay. Anytime we're talking about conics, conic section, an integral similar to this is going to show up. So you might say, well, what's the conic section? So depending on if you've been studying my material or not, some professors, colleges, campuses don't really cover conics too well. So conic section are things like ellipses, hyperbolas, um, things like that, right? What's the last one? Ellipse, hyperbola, and a circle, right? And a parabola. So those are all conic sections. When you study those, they generally, you'll see some form of this pop up. Okay, we'll cover conics more in depth later on in this text as well. Okay. So if we try to set up our integral, how we have it so far, it's going to look something like this. I have the x values for these ranges. So remember, x values are always cosines on the units on a circle, right? So pi over 4, right, or 1/4 pi is root 2 over 2 for cosine. And since this is not the unit circle, I'm extended by a unit of a. That upper bound, right, if we're going from smaller to lower, negative to positive, this is root 2 over 2 times a. Okay. 2 pi over 3. This is a 30, 60, 90 triangle, right? And the reference value for the cosine is 1/2. And since I'm in the negative value, this x value is negative 1/2 of whatever a is, right? So it's halfway between uh, a and 0. So that's in the negative direction. So that's how we found our bounds, right? We use the reference triangles for these nice reference angles that we have. And of course, I have to integrate the area under this curve from those values. Now, if you look at this, if you try to do this straight away, this does not look very nice, and it's not very nice, right? If I try to use, let's say, u is a squared minus x squared, that's not really going to help me because once I take that derivative, I'm going to have an x function, an x value inside of that derivative for du, and there's no x functions on the outside here, so there's nothing that's going to help me with that, right? So again, let's say I try to use a squared minus x squared. I get something like this, right? Negative 2x dx, which is fine. I can move the 2 over. But what about this x dx? It does not show up. There's no x on the outside of this radical sign. It is not going to work. I cannot use that substitution. Okay. not help us to integrate this function. So I have to use another approach, right? Which is substitute with the trig function, which should make sense to us because we're talking about a circle here. We know circles is how we kind of relate trigonometry with algebra, right? This going from this x squared plus y squared equals r squared and turning that into r cosine, r sine, tangents as needed, and things like that, right? So we're going to change our variable. Instead of talking about x's and y's, we'll go into sines and cosines, which involve angle measures, right? So we're going to change our variable to theta. So angles work much better for circles and ellipses, which is what we're working with. Obviously, I'm not going from one angle and then rotating to another one because I'm dropping straight down, right? So it's not starting from the origin and reaching out and then circling through and getting a sector of a circle. So this is a tad bit trickier than that, but it makes sense for us to go into talking about angles of some form, right? So again, in our example, it's clear that we start and stop on an angle measure on our circle for the area that we're looking for. So let's use the substitution x equals a sine theta. Okay. So if we take this and we use that substitution, right? X is a sine theta. If I differentiate both sides, right, I get dx a cosine theta d theta. And for my bounds, which was x equals negative 1/2 a, uh, I know that x is a sine theta, right? So negative 1/2 a is equal to x, which is the same thing as a sine theta. So now I can try to solve for theta. Divide both sides by a. Okay? I get 1/2. Negative 1/2 is sine theta. Take the inverse sine, right, or arc sine. And the inverse sine of negative 1/2 is negative pi over 6. Remember that the domain for sine or arc sine is from pi over 2 uh, to negative pi over 2. So it's quadrant 1 and quadrant 4. So yes, our measure is 2 pi over 3 in quadrant 2. But for inverse sine, we stick to the right-hand side of the graph, so quadrant 1 and quadrant 2. We're only thinking of positive values of x values, right, for that. So my reference angle for this, the thing that gives me the same values, would be negative 1/6. Okay, so that's our reference angle for using inverse sine for negative 1/2. So again, remember the domain for theta for arc sine or inverse sine is negative pi over 2 to pi over 2. For my other value, x equals 1/2 a root 2, which is coming from that pi over 4. Same thing. I set it equal to a sine theta. I can divide the a's right away, right, just like I did here. And so in order to find out what theta is, I'm just taking arc sine or inverse sine of this other value. Okay. So that gives me a value of pi over 4 as well, right? So that's very, very clear. We know that that from pi over 4, right? Root 2 over 2 basically is what this is. So I take my integral, and now I can make my substitution, okay? So my bounds, instead of going from the x values and having everything in x, I want to talk about everything in terms of pi, right? So my initial angle, right, value that I'm going to evaluate for theta is negative pi over 6. The terminal value is pi over 4, right? This is still a squared, and I substitute for x squared, which is a sine theta, and I'm going to square the whole thing. As we saw here, dx is a cosine theta d theta, right? A cosine theta d theta. So this a can move over here to the front. Remember, a is a constant value. It's the radius of the circle that I'm working with, right? So this is not a variable, it is a constant. The variable that we're working with is theta. Everything else is treated like a constant or a function of theta if indicated. So I'm going to go ahead and square my a and my sine squared here. So I got a squared sine squared. If you notice on the inside here, I can go ahead and pull out the common term of a squared. Okay. So now I have a squared that I pulled out. This is 1 minus sine squared. We know that this is the same thing as cosine squared. Right? And I'm square rooting now a product of squares. So this just turns into a cosine. But I'm also multiplying it times another a cosine. So that turns into a squared cosine squared. Right? Again, a squared is a constant term. So I could just pull that out. Now I can integrate cosine squared. Again, remember, we want to use those double angle identities. So this will be 1/2 times 1 plus cosine 2 theta, I believe. Okay. So I can pull out this constant now to the front of the integral, this 1/2. This turns into theta. And then here I can use a u substitution. So u is 2 theta. And that integrates rather easily at this point, right? So I know this turns into 1/2 sine 2 theta. The cosine turns into sine. We've already seen several times how to integrate something like this. So again, you can work that on the side to verify that if you need to. The 1 turns into theta. I'm still in theta, so I don't have to specify that these are angles, obviously. So I'm going to evaluate this then at negative pi over 6 to pi over 4. So again, we plug in pi over 4 first, and then subtract this negative pi over 6. So I'll have 1/2 a squared times pi over 4 plus 1/2 sine 2 pi, or I'm sorry, 2 times pi over 4. 2 times pi over 4 is the same thing as pi over 2. And we know that sine equals 1 at pi over 2. So I got the 1 pi over 4, 1/2. This should just be 1. Okay. I'm going to subtract from that. And again, this 1/2 a squared is in the front of everything. So I'm going to plug in my negative pi over 6 for theta. Okay, I'm subtracting this now. And I'm going to add to that 1/2 sine 2 theta times negative pi over 6, because the theta here is negative pi over 6. So that's negative pi over 3. So we're going to have 1/2. And that is negative root 3 over 2 for pi over 3, negative pi over 3. Okay. From here, go ahead and simplify everything. I have 1/4 pi plus 1/6 pi. So the common term there is 12 for denominators, right? So then this will be 3 on top, and this will be 2. So that should be 5 pi over 12. This 1/2 is all alone. These two multiply to the addition, or a plus sign, positive. 4 on the bottom, root 3. I could leave it here if I want to, or I could simplify more by pulling out the common term in the denominator, which I could have done in pretty much any other problem that we've done throughout this semester. So for something like this, I like to clean it up a little bit. So I'll pull out the biggest common denominator I can, which is 12. So this will turn into 5 pi. This will multiply times 12, so that'll give me 6. This will multiply times 12 as well, so that'll give me 3 there. So I have the 12 pulled out, and then I just kind of multiply everything by 12, so that if I were to bring a 12 back in, it would be equivalent to the 1 above. So this is fine as an answer. Okay, if you want to multiply the 1/2 through to everything, you can. I think this looks a lot cleaner, right? So I prefer seeing whole numbers when possible. Looks great, but again, whatever you want. Okay. As a mathematician, this is probably preferable, right? Instead of fractions everywhere. So we use trig subs basically whenever you see something that looks like a number squared plus or minus x squared. And so this first term squared doesn't always have to be a perfect square. It could be something very, very ugly, but it is some number, basically, right? A squared is just a constant. A constant squared is just a constant. So if this was like 3 plus x squared, yeah, 3 is not a perfect square, but still just a constant, right? So some constant plus or minus x squared. And that constant we're always going to consider as a square, whether or not it's actually squared. squared. Okay, so this thing that we're interested in could be in a numerator or it can be in a denominator. And if we see this, we are probably going to do a trig sub. Okay, so again, our goal is to kind of get rid of the root or whatever it is that we have on the inside by making that trig substitution and forming a perfect square where uh, things cancel out. So if we have the square root of a squared minus x squared, then we want to use x equals a sine theta. So again, whatever form, whatever constant is in there, you're taking the square root of that, and that is our value of a. Okay. So if I have something like this, um, my x value would be a sine theta. So then now when I square it, everything is squared. It matches with what I had in there already. I can pull out that as a common factor. I have 1 minus sine squared theta, which then I can use substitution for cosine squared theta. Take the square root, and it turns into a cosine theta, right? So that's kind of the idea of what we want to use when we see something of this form here, 1. Okay. And the domain here is that theta has to be between negative pi over 2 and pi over 2. If we have the same form, but instead of a minus, it's a plus between our constant and our x squared term, instead of a sine theta for the substitution, we use a tan theta, right? We use the tangent function. So if I do the same thing, a squared plus a tangent theta squared, square both terms, pull out the constant a squared term. Now I can replace this with secant squared, right? Square root, I have a secant theta, and the domain for the angle here is negative pi over 2 to pi over 2. The bounds not included. Okay, I'm not allowed to plug in uh, pi over 2 or negative pi over 2 into secant. That does not work. It's undefined. So open bounds on using the tangent. Okay. Also, it doesn't work in the tangent. These are the asymptotes for our tangent function. If I have x squared minus a squared, or let's say I just reverse the order. So, okay, the difference is positive a squared minus an x squared. Here, they're both positive. Here, it's the x squared minus the a squared, or equivalently, if I'm thinking about a squared being in front, it's negative, and I'm adding it to the x squared. Okay. So what we want to use here is the secant function for our x. And so when I replace, again, I'm going to use this part here. That's what we are sticking with. I'm going to get a squared secant squared theta. Pull out the common value of a squared. Okay? And we know that this is tan squared. So I have a squared tan squared. Square root of that is just a tan theta. And I'm using the domain closed bounds for 0 to pi over 2, which is open, or the closed bounds for pi up to 3 pi over 2. So this is the domain for theta for if we have to use secant theta. Okay. And again, that's coming from our substitution. If we have an indefinite integral, okay, so for our first example, we had a definite integral, we evaluated at some bounds, we had an actual value out, okay, we had the actual value that we calculated. If we are an unbounded indefinite integral, okay, we cannot leave our answer in terms of theta, right? We have to bring it back to the world of x. Remember, we started off with something in x. Here, you look at my example, there's no x's, obviously, because we have a value, right? But remember, I changed into theta. Go all the way back, I started off with an integral where the variable was x. Then I changed into theta. I did all of my substitutions and integrations, and then I evaluated at the bounds and got a value. Now, if there is no bounds, I can't just stop at something. I cannot stop at something in theta because I didn't start in theta. So whatever variable I started in, I have to end there also. So don't forget to substitute back. Now this tends to be the harder part. I will say when I first learned it, I didn't understand how people were getting these values. Now, obviously, I know. So I want to really, really emphasize that we have to get back to X, right? Do not leave your answers in theta. They will be marked wrong every time. So let's do an example, okay? So how do we do this? We want to make a right triangle based off of our substitution. Okay, whatever we use to substitute, we use that information to create a right triangle, and then all the information we need comes from that reference triangle. Okay, so let's go ahead and integrate 1 over 1 plus 9x squared. So again, it's not always going to have a square root sign, right? This could have been on top, and maybe something different on bottom. And we might have still needed to use a trig sub, right? But here, definitely we need to use a trig sub. There's no way for me to integrate this any other way that I know of or that we've taught here so far. A U sub wouldn't work. There's no integration by parts. There's nothing else for us to use at this moment, right? So uh, we have a constant multiple in my x term. Notice for all the rules, it was some number squared plus or minus x, right? A squared minus x. It didn't say k times x, right? Or a squared plus k times x squared. There's nothing times by x squared. It was always just a constant number plus or minus, and then my variable squared. So, here we go. Here's a little different because I have something times my x squared, right? It's not just a constant plus x squared, right? There's something with it. So since it looks different than what I'm used to, I need to manipulate my integrand until it looks like what I need it to look like, right? All of the cases that we went through above don't have a form like this. There's nothing times the x term. So first thing we do is we're going to manipulate our function so it matches the form of what we have a guide for, right? So how do I do that? Well, I can pull out a factor of 9, right? I haven't done anything illegal algebraically. 9 times 1 over 9 is 1. 9 times x squared is 9x squared, right? So I'm going to pull out this factor of 9. And then now, look, if you look at the numerator and the denominator, that's just the 1/9. That's just a constant. I can pull 1/9 out as a constant term to the outside of my integral. Now I have a single value of a squared, we'll say this, some number squared, plus an x squared that's all by itself. There's nothing with it. It's just an x squared. So you might have said, why don't we just use 3x? No. Okay. So my a squared is going to be 1 over 9. I need a, so I take the square root of both sides. A is going to be 1/3, not 3, right? So I'm going to have x equals 1/3 tangent of theta because I have some number plus my x squared. So this is the appropriate substitution to use, right? So now I'm going to plug in 1/3 tan squared, tan theta into x, and I'm going to square it, right? When I differentiate my x, I get 1/3 secant squared theta d theta, right? Because this is my substitution now. Because I'm going into thetas, so I can't just leave the dx and just put the tan thetas. I have to substitute this dx as well. So I differentiate both sides. So I still have my 1/9. This 1/3 here comes from the secant squared, so I'm just going to throw that on top. I could have thrown it on the side if I wanted to, but this secant squared d theta, right? 1/3 secant squared theta d theta. That all comes from the dx. On the bottom, I still have the 1/9. My x, right? I'm replacing with a tan theta. The a is 1/3, so this turns into 1/3 tan theta squared. I go ahead and square both of those, right? So I have 1/9 tan squared, and just like we needed, the number in front and the number here are the same. Now, if I had used, uh, if I had went here and used u was 3x squared, let's say 3 tan theta, it would not have worked very well, right? Or if I even used, yeah, 9, A is 9, right? So you can go ahead and play around with it. If you find another way that you think makes more sense to you, then that's fine. Easiest way is to get it to be identical to what you need, right? So that you can make the appropriate factorization substitution. So we're here. I'm going to pull out this 1/9. Okay. I'm left with 1 plus tan squared theta under a secant theta. I know that this gets substituted as secant theta. Okay. I can pull this 1/9 out. So this is in the denominator of a fraction, right? I have a fraction in the denominator of a fraction. So this really turns into 9. So I get 9 times 1 over 27, which cancels down to 1/3. I'm left with a secant squared over secant squared. So this turns into 1/3 integral just d theta, which we know is going to be theta. Okay. But I'm not done because, again, my original question was in terms of x's, right? So I can't just be like, oh, I'm done. I got an answer. I integrated and I did my constant. I'm done. We're all going to want to do that, but you have to remember to come back into the variable that we started with. So my substitution, if you remember, was this. X was 1/3 tan theta. So I can try to use this to figure out my value of theta. Right? X equals 1/3 tan theta. Multiply both sides by x. So now if I want to get theta alone, I take the arctangent or tan inverse, right? And I get tan inverse of 3x is my angle. So my answer then is 1/3, this exact thing, tan inverse 3x plus c. And that is how we integrate something like this with the trig substitution. So let's do another example. So let's integrate the square root of 1 minus x squared. So your first idea might be to say, can I factor this? And no, we cannot. This is not factorable. We have a 1 here. If there was a 2x here, um, then we could factor it, and that would be factorable. But we do not, except for the negatives too. That also throws us off. So you might be saying, well, this doesn't look like either of the 3 forms that we had previously, right? It's not an x squared minus some number. It's not some number plus x squared, and it's not some number minus x squared. There's a full-on third term. It's a binomial. It's a trinomial, right? Second degree. So what we need to do instead then is get it to look like the form we need. Something squared plus some number or minus some number. So if we complete the square, then we can get into the form that we are used to, okay? So if we identify all the parts that we need in order to complete the square, our A, B, and C, um, my A is -1, right? So again, remember, A is attached to the highest degree. It is not the first thing you see. It is the power attached to the power. My B is also -1. And my C that I have is 1. But remember, we're completing the square. So we're trying to find a new C. And so the values that we have, this one doesn't, it's not necessary for what we need to do until we find the new value of C that we're going to add and subtract. So when I throw it into the negative B over 2A, I get -1/2, right? Because this turns into a positive with the negative. A is also negative, so that's positive and a negative on the bottom. With the 2, that's 1/2. I take this thing and I square it, right? So when I square -1/2, I get 1/4. So what I'm going to do then is I'm going to add in 1/4 and I'm going to subtract it out right away, right? In case you don't remember how to complete the square, I'm basically adding in 0. I'm adding nothing, right? If I give you $1 and I take it away right away, you're not any richer, right? So it's a nice little math trick that we get to use in order to get what we want. So I haven't done anything. I've just changed the way that it looks. Okay. Um, so I'm going to group all of my negative stuff on one side. I can go ahead and factor that out when I need to. Um, and I'm going to factor this, right? I know what the factor is because it's always what I had here. So it'll be x squared, and then it's always plus whatever this thing is, and then I square the whole term. And so since I'm adding a -1/2, that's the same thing as saying x minus 1/2, square the whole thing, right? So, except that I pull out the negative, so now I don't have to worry about that since everything is positive, which is better for me. And so it's x plus 1/2 squared. So I have something squared, some number, and something in between. The thing in between that I have is a negative, right? So this looks like what I was doing, not here, right? Because it's minus the squared term. So that's our first part. We're going to use the sign sub, right? Some number squared minus my other thing being squared. So number minus something else, right? That's being squared. That includes my x, my variable. So I can make this as a substitution here, right? This 5/4 is going to be equal to my a squared. Before I do my substitution, I need to know what a is, right? So my a squared is 5/4. Square root both sides, I get √5/2, right? Or 1/2 √5. This is equivalent form. I need to make a sign substitution. And so my a sign is going to be equal to the thing that I have being squared, in this case, x plus 1/2. So from here, I just make my substitution. I don't have to do anything fancy here. I know you're like, well, do I get this alone? No, we're going to leave it how it is. I'm going to differentiate both sides, right? Because I need that d theta. I need dx to be substituted also. So differentiate both sides. The sign just turns into cosine, have the same constant multiple here. Okay, so 1/2 √5 cosine theta d theta. That's my dx. On the inside, I have my a sine theta. So 1/2 √5 sine theta. I square everything. So this turns into 5/4, right? This turns into sine squared. I can factor out that common 5/4. This I know is the same thing as cosine squared. Guess what I have over here? √5/4/2. What happens when I simplify this? √5/√4, which is √5/2. Okay. So first we look at the cosine. I can pull this out right now. I can pull it out then. It doesn't really matter. I'm trying to go slow because it's a little more involved, right? But when I pull out this constant term to the outside to separate it from the cosine, these things are going to go together, right? I'm going to get a 2 times 2, so I have a 4, and I have a √5 times √5 on top. So I'll just have 5/4. Okay, 5/4 on the outside. The square root of cosine squared is cosine times this other cosine gives me cosine squared. Here I use the half angle identity. 1/2 times 1 plus cosine of 2 theta. Okay, so that 1/2 comes in also, so this turns into 5/8. Here I could use that u sub. We also know it really just turns into theta plus 1/2 sine theta, right? So we've done this so much, plus my constant term. But the problem that we have here is that I am in the world of thetas, right? I need to get back into the land of x's. So I'll go to the substitution that I made initially. This x plus 1/2 is 1/2 √5 sine theta, and I will solve this for theta so that I can come back. So we always go back to our initial substitution, right? Our initial substitution is what we're working off of in order to resubstitute back, in order to build our right triangle, and all these kinds of things that we need in order to evaluate what we have. So if I separate this out, right, 5/8, this turns into 5/6. I need to start building my triangle. So I take my x substitution here, and I'm going to solve for sine of theta. So first thing that I do, multiply both sides by the reciprocal of this. Okay, so I'm going to have 2/√5 times x minus 1. I guess I'm slicker than that. I multiply everything times 2, and then I'll divide by √5. It's the same thing. It doesn't really matter, but it looks a little bit nicer. And then I take the arcsine or inverse sine, so I can solve for theta. So this is great, except for that doesn't really help me with this sine of 2 theta, right? I know what theta is. It's some convoluted looking thing, but what does that look like when I plug it into sine of 2 theta, right? So sine of 2 times this thing, right? So sine of 2 sine inverse, yada, yada, yada. That doesn't really make sense, right? So, which that's the part that used to get me when I was taking calculus 2 a long time ago. What we want to do, right, is we want to use this identity that we came up with, sine theta equals 2x plus 1 over root 5. We want to get this into simplest form. It already is in simplest form, right? This is the numerator. I just like writing those things on the side, as you can tell, right? This is the denominator. There's nothing else on the bottom. But we know sine from SOHCAHTOA is the opposite of our theta angle over the hypotenuse, right? Opposite over hypotenuse. So I'm going to build a triangle, right triangle. This is my angle. This is my right side. The hypotenuse is root 5, and the opposite side of my angle is 2x plus 1. Root 5, 2x plus 1. I have one missing side, okay? I want to solve my triangle out. I can call this A, okay? Um, whether it's the same, well, this part, it doesn't really matter. I can call it, I just don't want to call it X, right? I can call it A, R, K, M, L, whatever. It doesn't really matter. But A makes sense, right? A, B, C. So I use the Pythagorean theorem. A squared is 2x plus 1 squared equals 5. I want to solve for A. Do not multiply this out. Remember, you guys, I know algebra was a long time ago, but we want to work smarter, not harder. I just need to know what A is. So I'm going to subtract from both sides. It's 2x plus 1 squared, and I take the square root. I don't have to multiply this all out and try to factor in or any kind of craziness, right? This is good enough, um, right? I'll expand it out from here and try to get down to what I need to get down. Um, this 5 and this -1 can come together to a 4. It's a common term of 4 that I can pull out as a 2. Oops. Okay. And I have 1 minus x squared, which is the function we started with initially. Okay. So now I know what my value of a is. And so when I come back, I can now figure out the values that I need to for the sine of 2 theta. Okay. Our triangle turns into the following. Just replace this for my a. Okay. Putting everything together. Square root of 1 minus x squared is 5/8 theta plus 5 over 16 sine of 2 theta plus c. My angle, we knew from back here was sine inverse 1, basically 2x plus 1 over root 5, right? Or you could write it separate like that. So using this as my reference angle, and the identity that sine theta, cosine theta is the same as 1/2 sine 2 theta, right? I can use my half angle identities or my double angle identities. Simplifying this, I can multiply both sides times 2. And so now I know what sine 2 theta is. I can replace it with 2 sine theta cosine theta because I can answer those with these identities. It's going to be really hard for me to answer 2 theta using this. We can, but it's easier using an identity. So coming back, I have 5/8 times theta. So 5/8 times sine inverse, root 5 over 5, 2x plus 1. This is me rationalizing the numerator, the denominator, plus 5/16 times my 2 sine cosine, which is what I got for the sine of 2 theta, plus c. Using my triangle, because I'm still in thetas now, right? These are in x, that's good, but these are still in thetas. So I want to change for my sines and my cosines. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So now when I plug these in, 5/8 sine inverse, rationalized 1 over 5 here, and then this 2x plus 1. Again, you don't have to do all this. You can keep it as 2x plus 1 over root 5 if you want to. This is just the way that I prefer to write things. I have my 5/16 times 2 gives me now 5/8. My sine of theta is the 2x plus 1, the same thing that I had over here, right? That's the same thing I had over here, 2x plus 1. I'm just writing it appropriately, or more normally, I guess, for you guys. For this one, I'm going to go ahead and change it to this form so everything matches up. Times cosine, right? So I have my cosine function here, plus c. And so, um, again, this stays the same. This root 5 here turns into just 5, which cancels with this 5, which is why there's a 1 on top. This 8 and this 2 cancel out to give me 1/4. So here, all I'm left with is 2x plus 1. And here, all I'm left with is this 1 minus x squared square rooted. I cannot multiply this through. That is as far as I can take it. So now this would be my answer. Again, there is no thetas in my answer. Everything is back to x. I had to use my right triangle that I formed and that I solved for using the Pythagorean theorem. Again, plugging something in for sine of 2 theta using this would have been very, very difficult. So the goal is to try to get it back into sines and cosines. So I used my double angle identity in order to bring that back in, right? So again, I had 1/2 sine 2 theta, right? But that doesn't really help me because in my answer I had sine of 2 theta. So what do? I make this 2 sine cosine, right? And then now I can just substitute that straight in, and then I used my triangle. Okay. Thanks, you guys. Hope this was helpful. I will see you on the next video.